Hello students, welcome to Plus 2 Chemistry online classes. Today we discuss a new chapter from Plus 2 Chemistry, Coordination Compounds, our 9th chapter, Coordination Compounds. Okay, so this is entirely a new topic. We didn't study anything related to this chapter in 11th Chemistry. Okay, so in this portion, in this chapter, we are going to study what is a coordination compound and how the coordination compound is formed, what are the criteria required for the formation of coordination compound, then later to the bonding of coordination compound, etc. Okay, so today this is the first session of coordination compound. We can discuss the introduction of coordination compounds, like the basic things, basic terms related to the coordination compounds we can discuss in today's session. Okay, so after pausing this video, you can write down the notes. So children, you can write down the notes by yourself. Okay, so let's move on to the class. So let's start the chapter, coordination compounds. This is entirely a new topic. We didn't study anything about this chapter in 11th class. Okay, so let's start. So what is coordination compound? So coordination compound is formed by combination of a metal and ligand. Metal and ligand. Here M represents the metal and L represents the ligand. Ligand is a new term, so remember L represents ligand. So coordination compound, simply we can define coordination compound is the combination of metal plus ligand. Okay. And in this chapter we will study how we will select the metal and ligand etc. Okay. And this coordination compound is actually represented in a square bracket. It is formed by combining a metal along with a ligand, and this metal and ligand is represented in a square bracket. So that's the speciality of coordination compound. Okay. Always coordination compound is represented in square bracket, and inside the square bracket the metal and ligands were enclosed. So now let's see what is a ligand. Okay, we have studied the main two components of coordination compound. One is metal and other one is ligand. So now let's see what is a ligand. Okay, so this ligand can be a positively charged species or a negatively charged species, or it can be a neutral species. Okay, so remember, ligand can be either positive, negative, or neutral species. Okay, so this positively charged ligands were very rarely observed. Positively charged ligands were very rarely observed. And why positively charged ligands were very rare means that we can understand from the definition of ligand. From the definition of ligand we can understand why positively charged ligands we will not give more importance. So ligands can be defined as the electron-rich species. Ligands are atoms, ions or molecules. Ligands can be atoms, ions or molecule, but it must be an electron-rich species. It should have a lone pair of electron, or it must have electron to donate to the central metal atom. Coordination compound is formed by combining metal and ligand. How it combines means ligand donate electron to the orbital of metal. Ligand donate electrons to the orbital of metal. Thus a coordination compound is formed. Okay, and here metal is not using any electron for the bond formation. It just provides the orbitals, and to that orbitals ligand donates electrons. Okay, now let's see the condition for the selection of metal. All metals cannot be used for the preparation of coordination compound. We can prefer only transition elements, that is the D block elements is preferred in coordination compound as central metal atom. So remember, the central metal atom must be always a transition element. and ligand should be an electron rich species, okay, whether neutral, positive or negative. Then why we will prefer only transition elements? That is due to the presence of vacant orbital in the transition metal. Okay, we will prefer only transition metal in this coordination compound. That is due to the presence of vacant d orbital in the transition metal. D block elements consist of vacant orbital. To that vacant orbital, ligand donates electron, and that's why it can use in the coordination compounds. Okay. Now let's see the formation of coordination compound. Ligand donates electrons to the orbital of metal. Okay, that means metal remains inert during this bond formation. Metal just receives the electron donated by the ligand. It does not contribute any electron for this bond formation. And children, this type of bond already we have studied. This type of bond is called coordinate bond. Okay, so the bonding involved in coordination compound is coordinate bond. Metal and ligand pair join together through a coordinate bond. Coordinate bond normally we will represent with this an arrow mark. So coordination compound consists of coordinate bond, and the electrons were donated by ligands. Okay, metal just remain as inert. So keep in mind the bonding of coordination compound. Coordination compounds where exhibit coordinate bond. Now let's see some examples for the coordination compounds. Okay, here three compounds were written: CuNH3 4 times 2 plus. Next one is PtNH3 twice, Cl2, etc. So see this compounds, one is negatively charged and other one is positively charged, and the third compound is neutral. So in this first compound, NiCl4 2 minus, nickel is the metal and chloride is the ligand, and the second compound, copper is the metal and NH3 act as ligand. Okay, so NH3 act as ligand. And in this case, platinum is the metal. But here, two ligands are there. One is NH3 and other one is chloride. Okay, now please don't bother about the writing formulas of coordination compound. We will study that things later. So now just focus on this metal, ligand, etc. The naming and how to write the structure, etc. We will study in detail for in the coming classes. Now just understand this metal and ligand in a given coordination compound. You must be able to identify the metal and ligand from the given coordination compound. Okay. So now let's move to the important terms in coordination compounds. Okay, let's study some important terms in coordination compounds. Okay. So these are the important terms in coordination compound. First one is central metal. Always we are using the term central metal. Second one is ligand. Already we have discussed. And third one is coordination number. And next is coordination sphere. Okay. So these are the four important terms commonly we used in coordination compounds. So now let's see, consider this example. CONH3 6 times 3 plus. CO is cobalt. CONH3 6 times 3 plus. So let's see each component in this compound. Cobalt is the central metal. Here, cobalt is the central metal. Okay. And we can understand which one is ligand. Ligand is NH3. NH3. Ligand here, ligand is NH3. And now the new term, that is coordination number. Okay, so coordination number is the total number of ligands attached to the central metal atom. Total number of ligands attached to the central metal atom. Here it is 6. 6 NH3 is attached to CO. Therefore, we can say the coordination number of this compound is 6. Okay. So that's a new term, and this is actually important and that we will study separately. Okay. So just understand total number of ligands in a coordination compound is called coordination number. It can be 6, 4, 3 or any number, any whole number. And next one is coordination sphere, and that is nothing but this square bracket in which the metal and ligand is enclosed. The square bracket in which the metal and ligand enclosed is called coordination sphere. Okay, so I think you got all these four terms: central metal atom, ligand, coordination number, and coordination sphere. And you can see a 3 plus outside the coordination sphere. That is the total charge of this compound. Some of the compounds are charged positively, charged or negatively, and some of the compounds may be neutral. So this 3 plus here represents the total charge of this compound. Okay. So I hope it's clear. Central metal cobalt, then ligand NH3, coordination number is 6. So now let's see in detail the coordination number. Okay, this is actually the important thing in when we will discuss the basics of coordination compound. So generally it is represented as Cn. As short we can represent as Cn, coordination number. So just consider this example. NiCl 4 times 2 minus, just compound. Okay, each compound is having a different names. So naming we can study later. So now let's see coordination number. We want to find the coordination number of this compound. So coordination number, already we just defined coordination number, the total number of ligands attached to the central metal atom, or in another way we can define, it is the total number of donor site. Total number of donor site. Either total number of ligand or the total number of donor site. Okay, so don't get confused about donor site means the atom which donates this electron. Okay, so donor site. So here 4 ligands were attached to this metal nickel. So the coordination number of this compound will be 4. Okay, coordination number is 4. Now let's write another example. FeCN 6 time, FeCN 6 time 4 minus, FeCN 6 time 4 minus. And here when we will write this polyatomic ions, we will use a bracket. All those things we will study later. Okay, so Cn, 6Cn is attached to the metal Fe. So here the coordination number is 6. Okay, so coordination number, children understand, coordination number is the total number of ligands or total number of donor sites attached to the central metal atom. So next, classification of ligand. Already we just discussed the definition of ligand. So classification of ligand. Ligand actually donates electron to the central metal, that we already discussed. So based on the number of electron donated, the ligands can be classified. Based on the number of electron donated, the ligands can be classified into 3 types. Okay, there will be 2 classification for ligands, and first one, that is based on the number of electron donated. So mainly it is 3 type. So they are monodentate. First one is monodentate, and second one bidentate, and third one is polydentate. Bidentate can be written again as or didentate, monodentate or unidentate. That also we can use monodentate or unidentate. And here we will continuously use the term dentate, and this dendicity actually represents the electron donation. That means donor site. This dendicity means the capacity of what we will say, the donor sites that actually represent the dendicity, electron donating capacity. So what is monodentate ligand? A monodentate ligand should donate 1 pair of electron to the central metal atom. It donate not 1 electron, 1 pair of electron. Okay, and bidentate ligand, using this we can define bidentate ligand. It should donate 2 pair of electron. A bidentate ligand should donate 2 pair of electron. And next one is polydentate ligand. Any of the ligand, if it donates more than 2 pair of electron, that is considered as polydentate ligand. More than 2 pair of electron, if it donates, that's called polydentate ligand. Okay, so these are the 3 types of ligands: monodentate, bidentate, and polydentate. It should donate 1 pair, then 2 pair of electron, and more than 2 pair of electrons. Okay, Monodentate is also called unidentate and bidentate, didentate. Now let's see the examples of monodentate ligand. I minus, Cl minus, Br minus, now OH minus, F minus, then H2O, NH3, CO, then NO, etc. Okay, all these, some of the ions, some of the ligands were negatively charged and some are neutral species. All these ions actually donate one pair of electron to the central metal. So these all are considered as monodentate ligand. It's actually an important thing. You must know by seeing a ligand whether it is monodentate or bidentate. Okay, now let's see bidentate ligand example, ethylene diamine or ethane 1,2-diamine. We can write as ethylene diamine or ethane 1,2-diamine, which is a bidentate ligand. Okay. Very few bidentate ligands are there compared to monodentate ligand. The number is less. Okay, and we can write down this CH2, then NH2, and one more NH2 and H2. Okay, NH2. So ethane 1,2-diamine or ethylene diamine. So this is a bidentate ligand. Okay, and we can see that the name is actually too lengthy, ethylene diamine. So for the convenience, in coordination chemistry, it is represented as En, small letter En. Ethylene diamine is represented as small letter En. So this, since this is a bidentate ligand, it must contain two donor sites. It must contain two donor sites, or it should donate two pair of electron. So from this structure, let's see what are those two donor sites. This nitrogen contains lone pair and that will donate to the central metal, and this nitrogen. So the two nitrogen atom present in the ethylene diamine act as the donor site. And remember the symbol of En. Normally in coordination compound we will use this En. Okay. Now let's see the next example of bidentate ligand, that is oxalate ion. Okay. So bidentate or didentate, that term also in some cases we will use bidentate or didentate. So let's write the formula of oxalate ion, C2O4 2 minus, C2O4 2 minus, and its structure can be drawn as COO minus COO minus. Okay, so compared with the C2O4 carbon and 2 carbon and 4 oxygen, and negative charge is distributed to the two terminal oxygen. So these two terminal oxygen atom act as the donor site. Okay, so these two oxygen donates, each oxygen donates one pair of electrons, so totally two pair of electron. And that's why oxalate ion is a bidentate ligand. It donates two pair of electron. In coordination chemistry, oxalate ion is represented as OX. Okay, and sometimes C2O4 also used, and in some cases we could observe as OX. Next one is glycinate ion. Another bidentate ligand, that is glycinate ion. Okay. So let's write the formula of glycinate ion, CH2, then NH2, then COO minus, NH2 will be in the bracket. Okay, CH2, NH2, COO minus. So we can identify the two donor sites in glycinate ion simply, that is, one is this nitrogen and other one is the terminal oxygen atom. Okay. The atom which is capable of donating electrons to the central metal is called donor site. Okay. So since totally this compound donates two pair of electrons, that's why this is a bidentate ligand. Two donor sites were present. Okay. And this glycinate ion is represented as GLY in coordination compound. Very rarely we can find glycinate ion in coordination compound. Next one is dipyridyl. Next bidentate ligand is dipyridyl. DIPY is the representation, and this is the structure. And see, these two nitrogen act as the donor site. So this is also a bidentate ligand. Next we can discuss about polydentate ligand. The third category, polydentate ligand which donate more than 2 pair of electrons to the central metal atom. Okay. So only one example is given in the textbook about this polydentate ligand. That is the important one. The polydentate ion, example of polydentate ligand is EDTA. EDTA, the example for polydentate ligand. Okay. So let's write down what is this EDTA. EDTA is ethylene diamine tetraacetate ion. Ethylene diamine tetraacetate ion. And some of the cases instead of tetraacetate ion, ethylene diamine tetraacetic acid, like that also used. Ethylene diamine tetraacetate ion. Since this is acetate ion, this EDTA carries a charge of 4 minus. EDTA 4 minus is called ethylene diamine tetraacetate ion. Simple EDTA only, without charge EDTA is called ethylene diamine tetraacetic acid. So this is the structure of ethylene diamine tetraacetate ion, EDTA 4 minus. The structure of EDTA 4 minus is given here, not EDTA. EDTA 4 minus, so CH2, CH2. And how the structure obtained means by replacing the 2 hydrogen from ethane 1,2 diamine. Ethylene diamine, from ethylene diamine 2 hydrogen is replaced, and where acetate group is introduced. Where acetate group is introduced, thus we will get a structure like this. Okay. This is EDTA, and we can see EDTA, we already told EDTA is a polydentate ligand. And why EDTA is a polydentate ligand? Okay, this actually already discussed. EDTA means tetraacetic acid. Simply EDTA is tetraacetic acid, and if charge comes along with this EDTA, that's why it turns to EDTA 4 minus. And if no charge means instead of this oxygen, hydrogen will be there. Okay, COO minus, instead of that COOH. That's what acetic acid. So now we just focused on EDTA 4 minus. So this is enough. And the density of EDTA we should count. Density is the total number of donor site present in a coordination compound. Present in a ligand. So here we should find the density of EDTA. So since this is a polydentate ligand, more than 2 will be there. So these 2 nitrogen, and each 4 terminal oxygen atom carries a negative charge. That means they can also donate electrons. So in total, it consists of 6 donor sites. In total, it consists of 6 donor sites. Therefore, we can name this as a hexadentate ligand. Okay, this is actually a polydentate ligand generally, but specifically this is a hexadentate ligand. Hexadentate ligand. Okay, so this is about EDTA structure. So students, the structure of EDTA is important. So you must know the structure of EDTA along with the 6 donor site. Okay. This lone pairs also you must represent in the picture. So there are some questions from this topic. Very few number of questions were there, since this is an introduction portion. Number of questions can be done in the coming classes. Okay. So see the first question: why transition elements preferred in coordination compound? Write down the questions to the notebook and write it answers and post in the Google Classroom. Second, explain coordinate bond. Then write down the density of EN, OX, etc. And last, why NH3 is a monodentate ligand. Okay. And the classification of ligands, actually it's not over. That will be continued in the next session. Okay, so see you in the next video, and if you have any doubts regarding this topic, please mention in the comment box, and don't forget to read the textbook also along with this video. Read the textbook also. So see you in the next video, and thank you for watching.